Well, welcome back, everybody. In our last video, we talked about how to produce a soil report using the USDA's Web Soil Survey and what parameters to select after you'd identified your area of interest. And we started to talk a little bit about how to interpret those results, but I want to take a little bit deeper dive today into that. So what I have open here on the screen is the PDF that I received via email shortly after I hit submit on the cart on the Web Soil Survey. And you can see it's a nicely formatted PDF. It has a table of contents with all kinds of options there. So you can skip to different sections if you prefer, or you can continue to scroll down the page here. So we'll work our way down through. Obviously, it just gives you a look at the area of interest that you selected so that you have a reference point there. The preface of the report tells you all about soil surveys and how they were collected. Really kind of an interesting history if you've not dealt with them before. Obviously, your table of contents there showing you all the things that you selected when you were compiling the report. Again, more details about the actual collection process of the soil data and how the soil surveys are put together. Quite an incredible amount of work to map the soils of the entire United States. So the first element of substance here is the actual soil report, and we looked at that briefly as we put the report together and added it to the shopping cart in the Web Soil Survey. What you'll see here are the soil boundaries within your area of interest. And it's important to note because of the scale that these soil surveys were done on, and also the time frame that they were done in. They were done prior to a lot of our modern surveying techniques, certainly well before GPS. You're going to have some variability in these boundaries. So it's always best to verify what you're seeing in the report with what you have in the field, potentially by doing some test pits. Just a legend for the map here. Obviously, now we have our mapping unit names. As we looked at previously, the percent of the mapping of the area of interest that is in each particular soil type. And you can see here that the majority of our area of interest is in the Watson soil type. And then we'll get into a very detailed description of the soil types. Again, a lot of this is not terribly important. You're going to dial into the few parameters that are extremely important, but we'll just take a look at the Elvira silt loam here. The AV designation is the Elvira silt loam. The B is actually the slope. So if it's on a steeper slope, it would be a C. If it's a flatter slope, it would be an A. We get the elevation ranges, actually get the average annual precipitation, air temperature for the location, the frost-free period. So you can see there's just an incredible amount of data available for these soils. Again, some of it relevant when we're talking about the average annual precipitation. We can use that later to create the water balance for the pond, but in general, some of these things aren't terribly important to what we're doing. The typical profile is interesting because you can get a sense here, and this is very important for pond building, that your top 0 to 9 inches, your first horizon, is a silt loam, but as you get deeper, you get into a gravelly silt loam and then a very gravelly silt loam. So it looks like in this case, the Elvira conditions for pond building are going to degrade as you get deeper. We looked at the slope of the depth to the restrictive feature is how deep you go before you encounter something that inhibits water flow. So this is very important. We often hear people who say, well, I have an area in my property that lays wet. Will it be a good area to build a pond? And the answer is really, it depends. And this particular line here can give you some insight into that. So in this case, it says 15 to 28 inches to fragipan. A fragipan is a thin layer of clay that has water perched on top of it. So, what happens in many wetland situations is there is soil below the fragipan that drains well, and then this thin layer of very dense, tight clay that makes up the fragipan, and on top of that, water gets trapped. So if you have a rainfall event or if you have a drainage area upslope that contributes water down to that area, it will actually run along the top of the fragipan instead of percolating deeper into the groundwater. So it's really a separation between a very superficial groundwater feature and dry soil, followed by the actual water table. The depth to water table here can be very interesting as well. And this can tell you some things about what you might expect for incoming groundwater. It can also give you an indication that with a water table depth of 6 to 18 inches, that for most of the year, this will be a very challenging area to do construction work in for a pond. However, if you get into a very dry season, often that superficial water table fluctuates and you are able to get to that in dry conditions and do good construction. You'll also note that if you look at the depth of the fragipan at 15 to 28 inches, that this is actually that perched water table that we talked about, where it's just 6 to 18 inches below the surface. So it's sitting on top of that thin clay layer that makes up the fragipan. So again, we'll just get this level of detail for each of the soils in the report, which is very helpful. And as you're going through the planning process, gives you just a great amount of information that is very, very useful for that. So now we get into the classifications that we ran and selected the embankments, dikes, and levees to get the ratings for those. And we have a detailed description here of exactly what that rating entails. And as we talked about in the previous video, the scoring is on a 0 to 1 scale. 0 being that there are no limitations for the embankments, dikes, and levee construction, and 1 being that it is severely limited and we'll have to take some significant measures to improve that soil if we intend to use it for that purpose. Here's the visual representation of the ratings. Red, obviously very limited. Yellow, somewhat limited. If we had a green there, it would be not limited. And a map legend to go with that. And then we get a table that gives us all the reasons that a soil might be limited. And this again gives us a lot of really good insight into how this soil is going to behave if we use it to construct an embankment. Of particular interest here is the piping category. Piping is internal erosion in a soil. So if we build an embankment out of a soil like the Hartleton here, which has a piping limitation rating of 1, the worst that you can possibly have, it's very likely that the soil will create openings in the embankment. So we'll actually get channels that open up through the embankment and allow water to flow out. That those pipes, the soil pipes, start as a very small seep, and because of that internal erosion in the embankment, continue to get bigger and bigger and can actually cause the embankment to fail. So that's really a key thing to keep an eye on when you're looking at the limitations for embankments, dikes, and levees. The depth of saturated zone, again, that's not a major concern as long as you're able to plan your construction period out and know that you're going to do it in a very dry period. The large stones rating here in the Hartleton, again, a little bit of a concern. You might have to screen the soil to be able to use it and compact it. But the biggest concern here for that soil is piping. We really want to see that piping rating under a 0.2 for a soil that we're going to use in a pond embankment without any amendments, or in some cases, you might even get into using a geotextile fabric to support the soil and prevent that piping. So the next category that we looked at was excavated ponds, and these are aquifer-fed ponds that you can really excavate down and expect that they will connect with the water table. And because they're connected with the water table, likely have the water surface fluctuate. As the water table drops, your pond will drop. As it recharges and rises, the pond level will rise. So it's appropriate for some situations, and in some areas, the water table is more constant than it is in other areas. So this is just more informative than anything else. Again, as we look at the Elvira, we know we have shallow depth to water, but again, be careful, because if we do have that shallow fragipan layer of clay that's holding water near the surface, once we puncture that fragipan, it may be dry for the next 10 to 15 feet below that. So we really, the only limitation that we have here, because of the groundwater supply at this particular location, is depth to water. And we're familiar with this location, and certainly expect that if we were to dig a pond here, that it would be able to be fed primarily by groundwater throughout the year. So the next thing that we're going to look at is the percent clay. And this again, we pulled, and it's shown visually on our area of interest. And then it's broken down here into the percent of the soil that's composed of clay. So here we can see that the Elvira has nearly 25% clay, as does the Watson. The Hartleton is just at about 20%. For our purposes, we really like to get closer to 30% clay if we're going to build a pond without amendments, but that's somewhat subject to the water balance as well. If we have an excessive amount of water coming in, we can tolerate some seepage in the pond bottom, then we can tolerate a lower percentage of clay. And in an upcoming video, we'll talk in more detail about the water balance and how we develop that, and really how that's so important in the planning process of constructing a pond. And if you have a soil that's marginal, but you have a water balance that tips heavily in excess water, then you can save yourself a lot of money by not needing to amend the soil bottom or the soil in the pond bottom with a bentonite or a polymer or any other means. So we also looked at the percent sand. This just kind of gives us a little bit of a measure of the structure of the soil. Not a terribly important one to look at, but we've been in the habit of looking at it. There aren't any hard cutoffs here. We can always amend a sandy soil with enough bentonite to create a clay line pond. It's just a matter of the quantity required. That's often a case where we would want to do some detailed testing and do some hydraulic conductivity testing in the laboratory setting, so that we could dial in on an application rate for bentonite. So our saturated hydraulic conductivity, again, is a very important parameter and probably the most important one that we pull from the soil report to give us a sense of how water flows through the soil column when it's saturated. And if you remember, we picked the worst case scenario when we were setting this up. So we said return the maximum value for hydraulic conductivity in each of these soils and show that to us in a table. And here we have that table. The ratings are from 4.5 with the Elvira, 21.8 with the Hartleton, and the Watson comes in at 9.17. If you remember, the Hartleton was the soil that got increasingly gravelly with depth, so it's not surprising at all that that is a high rating there. The USDA breaks hydraulic conductivity out into 5 classes, starting with very low at 0.0 to 0.1 micrometers per second, low, which is 0.01 to 0.1 micrometers per second, moderately low, which is 0.1 to 1.0 micrometers per second, moderately high, which is 1 to 10 micrometers per second, high, which is 10 to 100 micrometers per second, and very high, which is 100 to 705 micrometers per second. So you can see that the Hartleton actually falls into the high category. We don't have anything at all that falls into the low or very low category, even the moderately low category. So we're moderately high with our best soil here. For comparison's sake, any kind of landfill liner is designed to be at 0.6 zeros and a 1 for the saturated hydraulic conductivity. So it's a really low value. For our purposes, we know that if we're going to get good compaction on a pond soil, if we get a saturated hydraulic conductivity of less than 1, we can build a very well-sealed pond bottom that with any kind of reasonable water balance will stay full throughout the season. Just as kind of a reference point, because it's kind of hard to understand micrometers per second, and that's a velocity of a water molecule through the soil pores. If we had a soil that had a saturated hydraulic conductivity of 2 micrometers per second, that would be the equivalent of that water molecule moving 5 inches over the course of a month. Now, that does not correspond to 5 inches of water loss because, of course, the water is only moving through the soil pores, not the solid part of the soil medium. So that's really, we saved the most important parameter to the end there. That's the crux of how you look at that soil data that you've returned from the Web Soil Survey. We are Natural Waterscapes. Our website is naturalwaterscapes.com. Our phone number is 877-493-7660. And you can always email us at support@naturalwaterscapes.com. We hope this video was helpful and look forward to the next video where we'll be talking about water balances and actually being able to determine if your pond will stay full.